Welcome. In this session, we'll explore nonlinear least squares problems. These are a set of structured problems that involve functions that have a common vector argument. So nonlinear least squares is usually abbreviated as NLS. And these are problems that have some number m of distinct equations. So it's a set of nonlinear equations. And all of the equations have the same vector argument. We have, in addition to m functions, we have m data, let's call them readings. And these are values that we'll represent as y sub I. We have m models, and these models are these distinct equations. So these are functions, and we'll represent them as g sub I, and they all have the same vector argument. And we seek an optimal W star. That is, we want a stationary point, or something close to a stationary point, that minimizes these all at once. And so what we do is we set our objective for this problem to be we'll want to minimize the sum of squares of residual errors. And so the nonlinear part is that these model functions are each nonlinear, and the least squares part is that we're going to take the difference between the values and the computed model, and we're going to square each of those and sum them, and that will produce a least squares problem. So that's where we're going. So what we'll do is we see a bunch of models, let's gather them in a vector. So we'll gather the models into a vector function. So this vector function will be g vector of W. We'll then formulate the residual vector. So the residual error vector, well, I'll just call it the residual vector. And that will be the residual. Now this will vary depending on the W that we provide to each of these model functions. So the residual, we will define that for this lecture as being the difference between the model and all of the given values that are gathered into a vector. So our objective for this is we will write this as capital F of W, and we will define this as being the sum of squares. Now, we're anticipating that a differentiation is going to be involved, and it's quite common when we anticipate a differentiation that we'll put a term of 1/2 in there so that certain things simply fall out nicely. So let's say it's 1/2, and if we say the sum of the squares of residuals, we can do that using the L2 norm, or the Euclidean norm. So we can simply say that this is the norm of the residual minus, the norm of the residual squared. So our problem then is we want a W star that is the argmin over all vectors in the vector space of this residual. So that is, in summary, how we'll formulate a nonlinear least squares problem. Now, let's see what a steepest descent would look like. Let's write our objective for this as 1/2, and we said it was the norm of the square of the residuals. That's an equals there. And we could write that as 1/2. One way that we could write this is we could say that that is RW transpose times RW. And if we differentiate that, then what we'll see is that the gradient of the objective function will be, we can imagine that there's an identity matrix in here, and when we do the differentiation using the methods from previous sessions, we'll see that that is the residual vector transposed times the Jacobian matrix for the model vector evaluated at W. And the direction of steepest descent, which will depend on the W, will be minus the gradient. So that'll be minus, and then we take the gradient of the function evaluated at the argument, and we transpose it from a one form to a vector. And this is often written as the negative of the Jacobian of the model evaluated at the argument transpose times R of W. I'll make two observations here. One is the full derivation is something that you can do, and you can also find it in the extra notes for this class. A warning is that there are two definitions for the Jacobian. There's the way that we did it, and then there's the transpose. And some authors will use the transpose Jacobian definition, and so they don't need the transpose, the Jacobian, when they're finding the direction of steepest descent. So if you go reading extra material, be aware, be careful to see how the authors are defining their Jacobian matrix, and then you'll see whether or not they need to have that transpose.